Hi guys, looking like we could use a little more review on limits and continuity based on what I'm seeing submitted in Google Classroom. So I want to put this video together for you. I just made a graph in Desmos with some discontinuities in it, and we're going to talk about limits and continuity as it relates to this graph. So first of all, I just want you to take a look at the graph. You see it's a piecewise function with 4 parts. The first part is the red, that's a parabola, or looks like a parabola anyway. It's a rational function. And the numbers in the brackets, so here, here, and here, are just the piecewise parts of it. So that's why we only see part of that parabola shape, part of the line, part of the hyperbola shape. So let's focus on the red part, specifically this fact that x plus 2 and x plus 2 are in the numerator and denominator. We know from the last chapter that if that happens, we have a hole. So even though we can't see it on the graph, which is typical, we know there's a hole when x equals negative 2, since it's at positive 2. So we know that there's a hole there. Whoops. And the fourth part of this function is just the point, negative 2, 4, so there is a point here. So this is still a function because there's a hole here, but a point there. It doesn't break the rule of whether or not something is a function. Let's look at the blue part of the function. So we see we have x plus 2 over x minus 2. And we know that that's a hyperbola, at least part of a hyperbola. And we also know it's a rational function that has the highest values of x and x. And since it's 1x over 1x, we know that the horizontal asymptote, as it continues in this direction toward infinity, is going to be 1. So this side of the graph is actually approaching 1. And then let's look at the third part of the graph, which is just the line that's in green. We would assume that it's going to continue this direction. So as it's heading toward negative infinity, the y values are also heading toward negative infinity. All right, so one other thing it might be interesting to note is where the red and the blue graphs come together. Because the blue graph is a hyperbola, and we see x minus 2 is in the denominator, we know that there is an asymptote, a vertical asymptote, at x equals 2. So lots of parts to this graph. I'm going to flip to the next page, and we're going to talk about some different measures of limits and continuity. So, based off of the ideas that we just talked about, let's talk about the limit as x approaches different points, starting with number 1. As x approaches negative 3, which is here, does the limit exist? And if so, what is it? Well, in order for a limit to exist, we know that it has to be approaching the same value. Whoa, I didn't mean to do that. I'm not sure how I did that. But we know it has to be approaching the same value from the left and from the right. And if we look at it coming from both directions, both of those seem to be heading toward a y value of 4. So the limit does exist, and the limit is 4 when x equals negative 3. Let's look at when x equals negative 2. So that would be here. We see there's a hole in the graph, but again, we're looking at this idea of what is the graph approaching. And so when we look from the left, it's coming this way, looks like it's heading towards a value of 1. When we look at it from the right, looks like it's also heading towards a value of 1. The fact that there is a hole there does not affect the limit because both sides are approaching positive 1. The limit exists and it is 1. This point up here does not matter because we're looking at what the graph is approaching, not where it actually lands. Okay, another point we want to look at is when x equals 2, which is here. So if we look erase this. If we look at it coming from the left, looks like it's heading up toward infinity. We know it's a parabola, so it's actually heading toward a point. But when we look at it coming from the right, we know it's heading toward infinity because we said there was an asymptote here at x equals 2. And so since the two sides are approaching different numbers, and since one side is approaching infinity, we know that the limit does not exist for two reasons. A limit can't exist when it approaches infinity. A limit can't exist when the two sides are approaching different things. To figure out what the red part of the graph would be approaching, we would plug 2 into this equation. We'd be able to figure that out. We don't need to do that for these purposes. I'm going to keep moving. Okay. The limit as x approaches negative infinity. So that's heading in this direction. We talked about that on the previous slide. This graph is heading down towards negative infinity. Negative infinity is not a number, and so therefore the limit does not exist there. In the textbook and the homework help, you'll see does not exist, but y is approaching negative infinity. They tend to qualify the answer. That's totally fine. Does not exist is sufficient. If we look at the limit as x is heading toward positive infinity, that's this direction. On the previous slide, we talked about the fact that there's a horizontal asymptote here at 1, and so we can assume that this part of the graph is heading toward 1, and so therefore our limit as x approaches infinity is 1. So I hope that helps a little bit with understanding of limits. The other part of this section is talking about continuity. So I'm going to erase all my marks here, and we're going to talk about continuity at a couple of points. Remember, there is a hole here. So when we look at f of negative 3, so here, is the graph continuous there? At negative 3, the green line does not have a value because it's less than negative 3. The red graph does have a value at negative 3 because it's equal to, and the value appears to be the same. And so even though it makes an abrupt turn, the idea of using the pencil test tells us that it's continuous. But in this chapter, we have 3 criteria we have to meet for continuity. So first criteria is, does the limit exist? Ooh, let me rewrite that so you can actually read it here. First criteria. Does the limit exist? The second criteria, is there a value at that x value? Is there a y value? And the third is, are the value and the limit the same? So let's use those 3 criteria to determine if there's continuity at negative 3. So the first question, does the limit exist? We said that earlier over here. The limit exists and it's 4, so we meet that criteria. Is there a value there? We see that here because there is a value. It's equal to 4 here. And are those two things the same? Yes. This function is continuous at that point. Let's talk about the point f of negative 2. So if we go through those same 3 criteria, well, first of all, let's just think about the pencil test. If there's a hole there or it jumps up to this point, we know from the pencil test it's not continuous. However, in this chapter, we need to use the formal definition of continuity to explain that. So using the formal definition, does the limit exist there? Yes, it does, because we said that here, the limit is 1. Is there a value at that, is there a y value at that x value? Yes, the y value is 4. But when we get to the third criteria, does the value equal the limit? No. So therefore, the function would not be continuous. And if you were using the formal definition of continuity, you'd need to write out these things. The limit exists, the value exists, but the limit and the value are not the same. If you were writing out your explanation for the previous problem, f of negative 3, you would say the limit exists, the value exists, and the value and the limit are the same. I hope that is helpful. As always, if you have questions, reach out to us. We're glad to provide further explanation anytime that you have questions.